Hello everyone. We're looking at topic 8.5 today, and topic 8.5 has everything to do with titration. So the way that titration works is you have a titrant, which we put in a burette. This burette has lots of calibration marks on it, and it's the known. Like, we know the concentration and we know the volume of the titrant that we are adding into the unknown. Okay? The titrant, or titrant, is either an acid or a base, and then the titrate down below is either an acid or a base, but it's the opposite because it's going to be a neutralization reaction. So if this is an acid, then this is a base, and if this is a base, then this is an acid. Where we keep our pH probe, if we have one, is inside of the titrate. Okay, so if something is reading pH, it's reading the pH of this guy down here. And yeah, that pH will change as we put drops of either the acid or the base in there. So we have titrant. This is known. We know what the concentration is, and we know the volume of liquid that we're adding. This is the titrate. This is our unknown. Yes, we have a known volume, but we do not know, it's unknown, what the concentration is of the item down there. And that's the entire point of completing a titration, is we're trying to figure out what the concentration of the acid or base is that is our titrate. Like I told you, you can use a pH probe to do a titration, or you can use an indicator. You can put a couple drops of an indicator into the titrate solution, and different indicators change colors at different points in their pH. So what the end point is, the end point of a titration is when the indicator changes color. Okay, so the end point is when the indicator changes color, but ideally we pick an indicator that changes color at the equivalence point. And the equivalence point is when the moles of the acid are equal to the moles of the base. Okay, that's the equivalence point. So let me clarify. Let's say that this is a base and this is an acid down here. When the moles of the acid that's down here is equal to the moles of the base that we add to it, then we have reached the equivalence point. Okay? Or we can flip-flop that. Like, if this is an acid and that's a base, then whatever the moles of the base are down here, when we add an equal amount of moles of acid, then we've reached the equivalence point. For a good titration, the end point, right, the point at which the indicator changes color, the end point is at the equivalence point. Okay, so again, summarizing this, the entire point of a titration is to calculate or find the concentration of the titrate. We use a burette that has the exact volume measurements, and we put something into that burette that we know the concentration. So this is known concentration and known volume that we're adding. That's our titrant. And we add this to a known volume down in our titrate, but what we don't know is the concentration. Okay, so from a titration, if we have a pH probe, then we can create or can be given a titration curve. and look at the axes of these titration curves. So in the y-axis, we have the less consistent item, the pH, and in the x-axis, we have the more consistent item, which was the volume of the titrant that we added, the thing that we were doing drops from the burette. So see how this is labeled strong acid and strong base? You need to be able to identify that just from the curve. So here's how we do that. First thing, don't forget that the pH probe is in that Erlenmeyer flask. Like, it's sitting inside of the titrate. And so it's reading a really low pH. We're reading something close to, if not below, 1 pH. That means that it's likely a strong acid. Okay? So I see this low pH, so that means that we got probably a strong acid that we started off with. And then we added a drop, and we added a drop of the base from the burette, and as we added those drops, the pH slowly increased, and then it really quickly increased, and then it tapered off again. And we ended at a pH that was pretty high. Like, anything like 12 or above, we could reasonably say that it was likely a strong base that was being added. Okay? The equivalence point, like I told you, is when the moles of the acid equals the moles of the base. And how you do this with a titration curve is, you see where it becomes really vertical? We go like halfway in between that. That's the equivalence point. Okay, that's our equivalence point right there. When a strong acid is titrated with a strong base, our equivalence point should be really close to a pH of 7. Okay, let's look at the next one. This is a strong acid with a weak base. Again, I would say this is a strong acid likely because it's got a pretty low pH. It's kind of hard to tell, but that like strong acid, lower pH. And then as we added drops of the base, our pH increased, then it dramatically increased, then it tapered off. But see how it didn't end super high? So this is a weak base that we were adding to it. But more importantly, see where it's kind of vertical? And if we go halfway in between that, that's the equivalence point. Anytime the equivalence point is below 7 for our pH, then that was a strong acid and a weak base titration, right? That titration was between a strong acid, which lowered the pH, and then the weak base couldn't bring it all the way up to 7. So if the equivalence point is below 7, then the titration was between a strong acid and a weak base. Now here we see a weak acid and a strong base. We're starting with a pH that is below 7, but certainly above 1 or 2. So we got this weak acid, and then we were adding drops of the base, so the pH increased, and it drastically increased, and then it tapered off, and it reached the pH that's probably the closest to the base, which is around 14 there, and that's a strong base. Like above 12, we're likely dealing with a strong base. But again, and more convincingly, if we find the equivalence point has a pH that is above 7, and only when the equivalence point is above 7 for the pH, that means the titration occurred between a weak acid and a strong base. All right, and then the last one. It's harder to see the equivalence point on this, but we're starting at a pH below 7, but it's above 1 or 2 there. So it's probably a weak acid, And then our pH ends above 7, so there was a base that was added for sure, but it didn't go super high. It didn't go like up towards 12, 13, or 14, so it was probably a weak base. And similar though to a strong acid and a strong base, a weak acid and a weak base have an equivalence point that occurs at a pH of 7. Okay, let's keep going. So if we turn the page, what would you say this titration curve is a titration between? Inside of the burette, sorry, not the burette, the Erlenmeyer flask. So inside the Erlenmeyer flask, well, we started with a pretty low pH. It started at a pH below 1, so it was probably a strong acid that was inside of that Erlenmeyer flask, right? And then it ends with a pH that's really high. It's like close to 12 or 13, so it's probably a strong base that was inside of that burette that we're putting the drops in there. And if it's a strong acid and a strong base, then the equivalence point should occur with a pH of 7. And yeah, it does look like the equivalence point has a pH of 7. Nice. Now you really need to be able to visualize what's going on here, okay? Like let's say right here, if we zoom in and we're looking at the molecules in there, what if we have this like acid, right? This acid, it has a hydrogen at the front. 1, 2, 3, 4, 5, 6, right? Like let's just say that we have a bunch of those molecules floating around in there, okay? And if I add a drop of that base, what happens is that the hydrogen, remember how acids are proton donors and like the base is a proton receiver? So if we put a drop of base in there, it can take that hydrogen away and we can be left with just that conjugate base, that A minus, like the hydrogen can be removed from it. And if we add another drop of that base, then it could do it to the next one. And then if we put another drop in there, that can remove the hydrogen from the next one. This is the half equivalence point, okay? Not the equivalence point. This is the half equivalence. And only at the half equivalence, the acid, the amount of acid is equal to the amount of the conjugate base, the acids that have lost those H pluses, okay? So not at the equivalence point, only at the half equivalence does the concentration of the acid equal the concentration of that acid's conjugate base. Something really cool happens here. Only at the half equivalence will the pH equal the pKa. And there's going to be a lot of questions about this. Like they're going to give you titration curves just like this, and then they're going to say, hey, for this acid, what's the pKa? And you need to find the half equivalence point, and then you need to look over at the pH, And you can be like, oh, well, I think for this acid then, at the half equivalence, it has a pH of 1, so then the pKa must be 1 for this acid. The best way to locate the half equivalence point is to find the equivalence point and to look at the volume at the equivalence point. And let's just say the volume read as like 10 milliliters. Then you want to find the volume that's half of that, 5 milliliters, and that's going to be your half equivalence. So we were adding drops of this base, and it removed the hydrogen from this one, and that one, okay? If we keep adding drops of that base, it will remove the hydrogen from this one, and this one, right? When we've added an equal amount of base as the acid that we started with, then all the hydrogens will be removed, and we'll just be left with conjugate base at that point, right? And so that's the other thing, is this is when, at the equivalence point, this is when the moles of the acid that we started with, okay, like the moles of the acid that we started with equals the moles of the base that we added. Because if we've added all that base, then all of the acid has reacted at that point. None of the acid is present anymore because we added an equal amount of moles of base that have then reacted and caused the acid to turn into its conjugate base. So the equivalence point is when the moles of the acid that we start with equals the moles of the base added. The moles of the acid that we start with equals the moles of the base that we added to it. All right. This one is similar, but there is a little difference. Are we starting with an acid or are we starting with a base? Okay, well, the pH is high, so we're starting with a base. And then we reach an equivalence point when we added our acid. Okay. Instead of drawing the particle view, let's do this. So just a reminder, and actually, do you know what? Let's save this. I want to see how you guys do with this in class. Let's talk through this to see if you're able to flip it when we're in class. Okay, I like that idea. There's going to be many questions where you have to do calculations for titration curves. And just a reminder, what we're calculating, what we're trying to find is the concentration of the titrate, right? Like, we are trying to find the concentration of the titrate. And there is a more complicated way of doing this, but I found a much simpler way that I want to share with you. But it's really important that if you use this simpler way on the free response part of the AP Chem test, that you do it in this manner, because there's things that we have to justify, that we have to show the graders that you understand. Okay, so here's the first thing that you have to put if you're going to use this method of calculating on the free response part of the AP Chem test. And the first thing that you have to put is moles of the acid equals moles of the base at the equivalence point. Like, you need to prove to them that, like, you recognize that, okay? And then the other thing that I need you to do is rearrange the concentration equation. So concentration molarity is equal to moles over liters. But we're going to deal with moles right now. So let's rearrange this so that it's something equal to moles. So if we multiply both sides by liters, then we know that liters times by molarity equals moles. Okay, so that's the background. Like, that's what we have to set up and show them that we know. And so moles of acid we could just rewrite as like Na, the moles of the acid. And if we're at the equivalence point, then this is going to equal the moles of our base. Okay, great. But moles are also liters times by concentration. So let's replace, instead of saying Na, let's say the liters of the acid times by the concentration of the acid, right? That's the same as moles of the acid. And then this would equal liters of the base times by concentration of the base. And this is so great because titration curves will always give you 3 of these 4 items, and then you just solve for the last one. So, for example, it says 50 milliliters of 0.1 molar sodium hydroxide, strong base. This was titrated with 0.1 molar HCl. Let's pretend like we're going to solve for that. We're going to try to figure out the concentration. Oh no, sorry. It's not this guy. It's this one. Let's say we don't know the concentration of the base. We're going to try to solve for that. And we do have the concentration of the acid that we were adding in there. Okay. So 50 milliliters of base. So the liters of the base was 50 milliliters, or 0.0500 liters. Okay. That was what was inside of the burette. Like, it was that many liters. We're going to find the molarity of the base. Like, that's what we're solving for right now. We want to know what the concentration of this guy is. The concentration, or the molarity of the acid that was inside the burette, we knew what it was before we put it in there. And that was 0.100 molarity. Okay? And we did drops and drops of this until we got to the equivalence point. Well, let's look. When we got to the equivalence point, that happened at 50 milliliters. So that would mean that the liters, or the volume of that acid that we added, was 50 milliliters, or 0.0500 liters. Okay. To solve for the molarity of the base, we just divide by the volume, or the liters of the base. So liters of the acid, molarity of the acid, divided by liters of the base. That's going to equal molarity of the base. So we're going to take 0.05 times by 0.1 and divide that by 0.05. Oh, well then, the concentration of the base was 0.1. 2 things, sig figs and units. This was a 3 sig fig number. This was a 3 sig fig number. That's a 3 sig fig number. Right now we only have 1 sig fig, so let's make that a 3 sig fig number. And if it's molarity, if it's concentration, then we need units of molarity, capital M, molarity. And that would be our final answer. All right, cool. let's do one more together. On the next page, page 20, it says 31.25 milliliters of 0.250 molar hydrochloric acid, okay, so strong acid, was titrated with unknown concentration of sodium hydroxide. The endpoint was reached when 23.75 milliliters of sodium hydroxide was added. Okay, unknown concentration of sodium hydroxide. So the liters for the acid was 31.25, so let's move that decimal to the left 3 times. So we have 0.03125 liters of acid. The molarity, or the concentration of the acid, is 0.250 molarity. Okay. Was titrated with unknown concentration of sodium hydroxide. That's a strong base. So the molarity, or the concentration of the base, is unknown. That's what we're solving for. And the liters, or the volume of the base. Okay, so here's our volume of the base. It's in milliliters. We need to change it to liters, so we'll move the decimal to the left 3 times. 0.03275 liters. Okay. The endpoint, right, or the equivalence point. So again, if this is a free response question on the test, we got to justify something. So we have to tell them that at the equivalence point, that the moles of the acid equal the moles of the base. Like, we got to tell them that we know this. And then we also need to show them that we understand that if we take concentration, which is moles divided by liters, and if we multiply liters to both sides, then liters times by concentration is equal to moles. So instead of saying moles of the acid equals moles of the base, instead we could say liters of the acid, concentration of the acid, equals liters of the base times by the concentration of the base. And we know liters of acid, we know the concentration of the acid, we know liters of the base, and we're solving for concentration of the base. So liters times by concentration for the acid divided by liters of the base. And then I'm just plugging that in. So our acid was 0.03125 times by 0.25 divided by 0.03275. 0.2385. Okay. Sig figs. I got 4 sig figs. I got 3 sig figs, 4 sig figs. So let's go with 3 sig figs. So this would be 0.239. And then what did we just solve for? Concentration, molarity. So capital M, molarity. All right, nice. We'll do a couple more of those practice problems when we get to class. And then this looks a little scary, but it's just an acid that has more than one proton, right? Like a monoprotic acid. Monoprotic just is like HCl. It only has 1 hydrogen. But a polyprotic, an acid that has more than one, is just like H2SO4. There's 2 of the hydrogens. And so if it's polyprotic, we just get a couple of bumps in our curve, depending on how many of the H pluses the acid has. So this one must have had 1, 2, 3 hydrogens, because there were 3 equivalence points on this curve. So not too bad. All right, see you all in class.